let's talk about linear momentum. Now, we're going to start with its definition, and when Newton actually got his laws of motion, and by got I mean derived, came up with, whatever you want to call it, he worked in terms of momentum. So what is it? Well, momentum is inertia in motion. Its symbol that we use is P, which doesn't make a whole lot of sense, but that's okay. And it is mass, the term for inertia, times velocity. Notice it has an arrow, and that's because momentum is a vector. You have to worry about what direction it goes. And it has units of kilogram meters per second. No fancy unit here, it's just kilogram meter per second. Mass in kilograms, velocity in meters per second. So how do we change an object's momentum? Well, we take the derivative with respect to time because we're interested in how it changes in time. We apply our chain rule. Oh, wait. Mass times derivative of velocity with respect to time, that's mass times acceleration. And then let's assume we've got a constant mass. Oh, wait, forces cause masses to accelerate. Forces also change an object's momentum. So external forces change the momentum of a system. This is the most important equation that we're going to be dealing with. And by equation, of course, mean concept, because equations come from concepts. Apply an external force, change an object's momentum. Now, when we're looking at forces changing momentum, we look at this term called impulse. So I'm going to put the dt. So a force times a little bit of time, exerted for a little bit of time, is equal to a small change of momentum. If we integrate this, I can get the integral. The change of momentum is equal to force times delta t. If this is time dependent, of course, you've got to integrate the whole thing. But if it's consistent, if it's a constant force, if the force is constant, you can just use delta t. So forces exerted for times change momentum. Let's give an example how we can use this. We've got a person on a trampoline, and we've got another person. Over here, this person's going to hit the ground, this person's going to hit the trampoline. They have the same velocity, which means that they have the same momentum. And if they come to a stop, that means that delta p, and I'll make this solid ground, delta p is the same. Now this person, right here, person 2, has a little bit of force because they have a big delta t. This person over here has a lot of force because they have a small change in time. Ground stops you pretty abruptly. So what this tells you is that if you want to change an object's momentum, for terms like safety, try to extend it over as long as possible. Same thing, follow through when you swing a bat, crumple zones on cars, all of those are designed to minimize the force because your change in momentum is going to be the same when you're going however fast and you come to a stop. Let's look at a couple examples. So in this first example, I give you a function for momentum, and I want to find the force. Well, I know that forces change momentum with respect to time, so let's differentiate with respect to time. And you get 12t squared, kilogram meter per second fourth. This just makes sure that your unit of force is the Newton. All right, so to find force, take the derivative with respect to time. Makes sense. If you want to find its position, well, let's look at the definition of momentum. Mass times velocity, and I know velocity is dx dt, change in x over change in time, or derivative with respect to. So let's move this dt over to that side and integrate. And when you do this, we have plug in our initial boundary conditions for position and time. And then what you get is an expression of where you're going to end up. So if you're interested in position, use the definition of momentum and know that v is dx over dt. And integrate, just like we were doing all the time before when we were looking at accelerations, velocities, positions. Pretty cool. Now for another example, we're going to look at impulse. So I've got a baseball. It's going to go in, and this baseball is only going to travel in the x direction for simplicity's sake. If you have multiple components, you'll need to break it up into components. So I know force is caused by a change of momentum. I'm looking at an average force, which means I can use total change of momentum over in total time. Change in momentum, mv final minus mv initial, over delta t. Keep in mind, I need to figure out which way is plus and which way is minus. In this way, I set up that I set this as my plus x axis. So my final momentum is negative, my initial momentum is positive, which means that my force is negative 1929. Remember this negative? All it is a direction. which makes sense because if I want to change its momentum, the direction of the change in momentum is equal to the direction of the change in force. So we've talked about impulse, we've talked about momentum, we've talked about what it was. When we come back, we're going to discuss what happens if you don't have external forces. All right, well, I hope this helps. I will see you in class.